So explicit formulas aren't the only way to write the formula of a sequence. We can also have recursive formulas, also known as recursion formulas. Basically, a recursive formula defines the next term based on the value of its previous term or terms. So we're basically writing a sub n as a function of a sub n minus 1 and or a sub n minus 2 and so on. And there's something called a recursive definition. So the recursive definition of a sequence, it has an initial condition or conditions and a recursive formula. So we're going to see an example of that right now. So for example 2, find A4 for the sequence an equals a sub n minus 1 plus a sub n minus 2, where a0 equals 0 and a1 equals 1. So notice how I'm starting the index of the sequence at 0 now. So that's totally valid. If I want to find a4, what do you think I should do? If I have this formula and I want to find a4, what is your gut telling you should do?
Plug in.
So you might think, I'm going to plug in 4. So I get a4 equals a sub 4 minus 1, so that's a3, plus a sub 4 minus 2, so that's a2. But we don't know what a3 and a2 are. We just know a0 and a1. So before we go straight into a4, we need to find a2 and a3. So I'm actually going to start by plugging in 2. I'm going to get a2 equals a sub 2 minus 1, which is a1, plus a sub 2 minus 2, which is a0. So a2 equals a1 plus a0. So a1 is 1, a0 is 0. So we have 1 plus 0. So that means a2 equals 1. So now that we have a2, let's find a3. So a3, when n equals 3, a sub 3 minus 1, that's a2, and a sub 3 minus 2, that's a1. So a2, we just figured out, is 1, and a1 is given as 1. So what's 1 plus 1, guys? It's a tough one.
1.9999 repeating.
Perfect. Yes, it's 2. Same thing. So
only real ones to get that reference from a previous video.
Yeah. So now that we have a2 and a3, we can finally plug in 4 and find a4. So a4 equals a sub 4 minus 1, so that's a3, plus a sub 4 minus 2, so that's a2. So a4 equals a3, which we just figured out is 2, and a2, which we figured out earlier is 1. So a4 is 2 plus 1, which is 3. So that's a recursive formula. So that's different from an explicit formula, right? Because for an explicit formula like this, you just plug in 5, for example, and you get a5. But for a recursive formula, the terms depend on previous ones. So you can't just plug in 4 and immediately get a4. You need a3 and a2 and so on. So that's why we need these initial conditions. Okay? So this sequence has a special name. Do you guys know what the name of the sequence is? Where the next term is the sum of the 2 previous terms?
Is it Fibonacci's?
Yes, the Fibonacci sequence. Good. So the Fibonacci sequence, I'm saying a0 is the first term, so it's 0. Then a1 is 1, a2 is also 1, a3 is 2, a4 is 3. Without me plugging in numbers, you guys might be able to see what the next term is going to be, right? It's going to be the sum of the 2 previous terms, which is 5. And what would the next term be?
8.
Yeah. And one last one. What would the next term be?
13.
Yeah. So each term is the sum of the 2 previous terms. So that's what this formula is saying, is a sub n equals a sub n minus 1 plus a sub n minus 2. Okay, so very important sequence, the Fibonacci sequence.
We add a sub n minus 3 and make it like a super Fibonacci sequence.
That would be interesting. We can definitely do stuff like that. Anyway, so that's it for example 2. The next sequence we're going to talk about are geometric sequences. So this is a very important and special kind of sequence. So this is where each term after the first is obtained by multiplying the previous term by a non-zero constant r. So r is called the common ratio. So the first term is a, the next term is r times that, and then the next term is r times that, and then the next term is r times that. So it's r times the previous term, basically. So let's do example 3. Write the general, explicit, and recursive formulas for a geometric sequence. And then it gives this sequence here, and it's asking, is it a geometric sequence? So let's start with the explicit formulas. The formula changes a little based on how you start the index. So let me start the index at 1. So let's say the first term is a1, which is a. The second term is a times r, right? R times the previous term because it's a geometric sequence. The third term is r times the previous term. So r times r, you get r squared. So this third term is a r squared. The fourth term is a r cubed, and so on. So I want to create an explicit formula for this sequence. Basically, what is a sub n as a function of n? So do you guys notice something interesting about the subscript and the exponent? There's a pattern going on. So this is really a times r to the power 0, right? Because r to the 0 is 1.
It's all one less.
Yeah. So notice how the exponent is 1 less than the subscript. This is 0, this is 1. This exponent's 1, and the subscript is 2. Over here, the exponent is 2. The subscript is 3. So the exponent is always 1 less than the subscript. So if the subscript here is n in general, we're going to have r to the n minus 1. And these all have an a in front of the r to the power of n minus 1. So I'm going to keep that there and put an a. So that's the explicit formula for a geometric sequence where the index starts at 1. So if I plug in 4, for example, I'm going to get a times r to the power of 4 minus 1. So a r cubed, which is consistent with what I wrote. So just keep in mind that n starts at 1. It's a natural number. Do you guys know what this symbol means? It means n belongs to the set of natural numbers.
It's like an element of the set.
Yeah.
Also looks kind of like a currency.
Yes. We can do the same thing, but the index starts at 0, and you'll get a slightly different formula. So if I say a0 is a, and a1 is ar, and a2 is ar squared, a3 is ar cubed, and so on. Again, this is really r to the power of 0 here. What do you notice about the subscript and the exponent now if I start the index at 0?
Oh, they're the same.
They're the same, yeah. So,
That's much prettier.
so the formula, instead of an equals a times r to the power of n minus 1, it's just a times r to the power of n if you start the index at 0. So this is for n belongs to the set of whole numbers. Okay, the problem also asks for recursive formulas. Now we want to write a sub n as a function of the previous terms. So notice how a sub n in general is r times the previous term, right? So the previous term, the term right before a sub n, is a sub n minus 1. So a sub n is just r times a sub n minus 1. And that's it. That's the recursive formula.
That was nice.
Yeah. I hope you guys understand the difference between explicit formula and recursive formula. This is writing a sub n as a function of n. Like I plug in 5, I get a5. But for this one, we're writing a sub n as a function of the previous terms. So I'm saying like a5 is r times a4. Okay? You can also do this another way. You can say a sub n plus 1 is r times a sub n. Right? Same idea. The next term is r times the previous term. Okay, and the last part of the question is a sub n plus 1 divided by a sub n equals 2 plus sine of n over n a geometric sequence? So does anyone have any idea how you'd go about this problem?
Well, it has to have r being a non-zero constant.
Yes. Very good
Less
point.
Not sure I see a non-zero constant multiplier.
Okay, that's a very good point. So notice how in this recursive formula, I can divide both sides by a sub n, and I'll get a sub n plus 1 divided by a sub n equals r. So that means if I divide two terms that are right next to each other, I should get a constant r. For a geometric sequence, is that what's happening here? A sub n plus 1 divided by a sub n? Am I getting a constant?
I think it may not be.
Yeah, so this is not a constant because it depends on n, and n varies. Sine of n over n is going to change as n changes. So this is not a constant. So that means this is not a geometric sequence. There is something interesting about this sequence, though. What happens when I take the limit of a sub n plus 1 divided by a sub n as n approaches infinity? When n approaches infinity, what does this approach? Like this 2 is not going to change as n approaches infinity. It's a constant. But what's the limit of sine of n over n as n approaches infinity?
For sine of n over n, would it just be 0?
Good, yeah, because sine of n just oscillates between -1 and 1. But n is going to approach infinity. And when the denominator gets really big, this is going to go down to 0. So the limit is just 2. So that's interesting. When I take the limit of a sub n plus 1 divided by a sub n, I get a constant 2. So do you guys know what that means? So even though this is not a geometric sequence, as n approaches infinity, it eventually behaves like a geometric sequence because each term is about double the previous term. Do you guys know why I'm doing this, by the way? Why I'm taking the limit of the ratio of the consecutive terms?
To torture us?
A little bit, but this will be important when we learn about the ratio test. This will be important for later. This is also jumpstarting the calculus that's coming up.